With the help of this product of science, you are watching this program, the first in a number about the physical sciences, responsible for the understanding of natural laws which made this camera possible. I'm Philippe Le Corbeiller of Harvard University. At Harvard, I am at times an applied physicist, but at other times I am expected to present the essentials and also the spirit of physics. Two roles I will not forget as I appear here each week as your host. In the next few minutes, you'll see for yourself what you can expect of me and my colleagues, and also, by the way, what we will expect of you. In a moment, Gerald Houghton will give you some idea of these great expectations. But now, since this is a television program and not a one-sided conversation, we should have titles. May we see them?
I won't invite you to watch an atomic explosion, and I won't give you a formula for turning lead into gold, but I can invite you to participate for the next 23 weeks in some hard thinking. A great deal of science is just that. I would delude you if I told you it was easy, but that is just what you'll find exciting, how one solves difficult problems. What is science? What are some of its great achievements? What is a scientist? What are the questions which really excite him? And how does he go about getting his answers? Sometimes a scientific explorer suddenly finds himself on new ground. What does he do then? 3 centuries ago, the Italian scientist Torricelli was in this situation. Common sense and science both said there could be no such thing as a vacuum, a space totally empty. But Torricelli found observations which flew right in the face of common sense. For example, in the behavior of a mercury barometer. Here, I want you to drop in on the chemist Leonard Nash when a few weeks from now, he will be showing Torricelli's argument. And it is typical of the methods of scientists before and afterwards, even if it merely seems to involve the behavior of some mercury in a glass tube.
The idea of using mercury in a barometer occurred first about 1640 to a young associate of Galileo's, Torricelli by name. Here's Torricelli's experiment. A 3-foot tube sealed at one end, filled with mercury to its very top and open here at the top. I put my thumb over the top and then, dexterously we hope, invert it in a pool of mercury. What happens now when I remove my thumb? Watch. The mercury falls. And what is left in the top of the tube? Might this region be empty? Could it really be a vacuum, that which had been supposed not to exist? Torricelli observed that if you tip the tube, the mercury runs up it without meeting any resistance. Nothing then at the top of the tube resists the motion of the mercury. That looks as though the top of the tube might indeed be empty. It's possible to confirm this tentative judgment even more strikingly by adding water at the bottom of a barometer set up exactly the same as that which we made ourselves. Mercury at the bottom, water layer floating on top of it. And now I propose to pull this barometer tube up out of the mercury into the water. Let's see what happens. The water rushes up, displacing the mercury, which falls down toward the bottom. And ultimately, if we're fortunate, we can fill pretty nearly the whole tube. It fills the entire space, and you can surmise that the space at the top of this tube was originally a vacuum. Torricelli went on then to show that mercury stands at the same height in tubes with either large or small vacuum spaces, and that in all cases, the height of the mercury column is 29 inches, very nearly 2½ feet. Now, what do you make of that?
What do you make of that? Well, of course, you will first have to see the experiments and the theories in their order context, and you will want to hear the outcome when you watch in a few weeks. In fact, when seen without proper preparation, the work of a man in the laboratory does not have a pattern or an order, and this is characteristic also of all the raw information which comes to us from the world around us. All our information comes to us as flashes of light and color, sounds and other sensation, a disconnected series of impressions intruding on us like rain hammering on a window. Our task is to find an order in this chaos, or as William James called it, this buzzing, blooming confusion. Here we stand, just halfway in size between the unimaginably small parts which make up our bodies and the awe-inspiring vastness of the setting for our lives. And what makes man great is his habit of asking great questions. What is truth? What is goodness? What is beauty? But also, what is the world like? What laws govern it? How can one tell one another about it? If you look up into the sky, what you really see is not a firmament of fixed stars or a celestial sphere. What you do see is a disorderly array of pinpoints of light. And yet, astronomers have found a marvelous order. Some weeks hence, the astronomer Bart Bok will trace out the structure and size of the solar system and indeed of the universe. Here, he'll take us out from our Earth to our moon, across the solar system, to the Milky Way, to the neighboring galaxies scattered like pinwheels through space, to the very farthest parts of our still expanding cosmos. This is our way of looking at science. Science as it appears to the astronomer, the physicist, the chemist, the geologist. The important thing about science is not merely that it gives rise to technological miracles, but that it provides us with one of many guidebooks which we need to find our way and our place in this universe. And as you watch our programs unfold, I think you'll discover too why we try not only to give the answers which science has for these grandiose questions, so many miles, so many years, but also we want to bring out how a scientist goes about doing his work, with what tools, with what habits of mind. You see, the word science has two meanings. On the one hand, it means the accumulated knowledge, the hard-won catalog of facts and laws and theory. The catalog built up by many men from the time of Copernicus to our own. You could call this the public side of science. The results you can look up, neatly set down in some textbook. But on the other hand, there's also the private side of science, the personal activity. When a scientist publishes his result, he has to speak in terms of facts and figures and logical sequence of thought. But while he's actually working, he often proceeds like an explorer through an uncharted jungle, sensitive to every sign, with every faculty of his being, reacting to almost imperceptible clues with unreasoned responses. How does he do that? How does he react, and what is important to him? This is why we chose the title of Science and Scientists. And this is why you'll hear often of the great conceptual revolutions in science, the times when a handful of men, perhaps, had to remake a whole body of knowledge. The most famous case, of course, is that of Copernicus and his conception of the sun-centered universe. It is an idea which is so completely contrary to common sense. The idea that we live not on some fixed planet, but rather on a little Earth which rushes through space at the speed of 70,000 miles per hour in a path around the sun. To this day, we still feel that this is preposterous. For if it were true, then, for example, a ball or any object thrown straight up in the air should not land in my hand, but should land far behind. For I am fixed to the earth, but the ball, when it is in the air, is free. And being free, it can fall behind as I rush forward with the spinning earth around the solar system. But the fact is that what seems intuitively clear is simply wrong. And what's more, we can prove it. The historian of science, I.B. Cohen, will show you this experiment. We put this golf ball in this cart. There's a spring inside which can toss the ball high overhead when the cart moves. Now the cart goes on a track, a special track which has a device in it to release the spring and to let the ball fly upward. Now suppose you move this cart down the track. Will the ball land behind the cart or in it? Watch this slow motion picture. As you'll see many times, experiments can help us forward when ordinary common sense misleads us. But it's not always so easy. Can you prove that atoms exist? Can you prove that by experiment? A golf ball is real enough. But there is no way of observing an atom directly. Is it real? Or is it merely a useful fiction? And what is reality anyway? That which we see and experience directly, or what we take to be the underlying structure out of which experience arises? Or perhaps both. Are these particles science uses, atoms, ions, electrons, alpha rays, are they real? Now, industrial chemists and nuclear engineers can successfully use this idea of atoms in their work. That's one kind of proof. But as the physicist Edwin Kimball will tell you in a few weeks,
this is pretty impressive proof of the reality of atoms, but we can do better. We can see the track made by a flying alpha particle. As these particles fly through the air, each leaves behind it a trail or track of positive and negative ions. These ions are as invisible in an ordinary microscope as the alpha particles themselves, as invisible as all individual molecules, atoms, or subatomic fragments. But there are ways to convert the invisible trail into a visible one. One way, developed by C.T.R. Wilson, is to allow the ion trails to form in chilled, moist air. For example, let me blow on this piece of cold, dry ice. You see that the moisture of my breath forms a cloud when it's chilled. The chilling creates a fog by condensing water vapor into a multitude of tiny, visible drops of water. If there are ions present in such moist air, the water drops condense on them first. If these ions are distributed along the trail left by an alpha particle, the water droplets form a line or track where the alpha particle passed by. To observe these tracks, you can build a glass-enclosed cloud chamber, similar to this one. Inside, the tracks are easy to photograph. They frequently tell interesting stories. Here, for example, is an ion trail photograph showing a pattern of alpha tracks from radioactinium. Here is a similar group of tracks from radioactive polonium. Here you can see what happens when the tracks form in the field of a large electromagnet. The bending of these tracks is due to the interaction of the charge carried by the alpha particles and the magnetic field. It proves that the particles carry positive electric charges. Now suppose the radioactive material you use as the source of alpha rays is itself a gas mixed with the air. In this case, the spontaneous explosions which eject the rays can start anywhere in the chamber and may move in any direction. Here is a single track from an atom of radon in such a chamber. In the case of thoron, another radioactive gas, the explosions occur in pairs in rapid succession. Hence, we observe pairs of trails diverging from a common point. Let me inject a little thoron into this cloud chamber. At first, you see a cloud formed by confusion of ions as the gas enters. Then, as the gas distributes itself out a bit, you can see pairs of tracks. Each pair of ion trails is automatically transformed into a pair of water drop trails, sharply defined at first and then slowly fading. And now, if you still have a lingering skepticism about the reality of atoms and molecules, you might ask yourself the question, what are those tracks? What makes the Geiger counter click? How can such effects occur if matter is not composed of atoms?
Even in that brief preview, you can see that the kind of arguments that are important to a physicist. And there was a philosophical problem here also. It is this: how can one know anything about things not directly accessible? How can one find out what there is in a black box which cannot be opened? Many questions of science are just of this kind. What is there in the interior of the earth? What is there far below the deepest mine shaft, the deepest oil well? And how do you go about finding out? With problems of this kind, there is usually just one method of finding an answer. And as an example of this method, you'll see the geologist Kirtley Mather explain the usefulness of earthquake waves.
We call these surface vibrations long waves, L waves for short. Now there are others that go deep into the body of the earth. These are of two kinds. One kind we call the P wave. P for push and pull. Such a wave pulses to and fro along the path of transmission of the wave. We'll call that the P wave. Now the other kind is the S wave. S for shake or shear. It is transmitted by a transverse vibration, the S wave. Both kinds of waves, P and S, travel along the same paths deep into the interior of the earth. But S waves move only through a solid, since only a solid resists the change in shape which this sort of wave involves. Both the P and the S waves, going deep into the interior of the earth, move in paths that are curved because of the differences in density, in elasticity, of the earth materials. These waves travel at different speeds, and hence arrive at stations at identifiable times. Here's a model. Part of the earth cut away. And you can see from it that the farther the recording station is, one here, earthquake origin over here, the farther the station is from the earthquake origin point, the deeper into the interior the wave must have gone to reach that recording device. The deeper the wave goes, the faster it goes, according to hundreds of thousands of records taken on seismographs around the world. Now, this increase in the velocity of the wave with depth shows that there must be an increasing elasticity in Earth materials with increasing depth. However, there is a depth at about 20 miles or 30 miles under the surface below which the waves move at about the same velocity, regardless of whether they move under the continent or under the oceans. For the speed of travel increases with greater depth. It does so at just about the same rate everywhere the world around. This is good reason for believing that rock materials at depths greater than 20 or 30 miles are everywhere just about the same. From all this, we infer that the Earth's interior looks something like this. Concentric shells of rock of varying density, generally increasing in density with depth.
What is inside the Earth? We cannot, of course, find out directly by traveling there. Are atoms real? We cannot find out directly. They are too small. How large is the universe? We can't measure it directly. We are bound to our tiny Earth. So unable to make direct observations, unable to simply open the black box and look inside, scientists often have to get their information in the most astonishingly indirect ways. This indirectness, you see, is what makes science look sometimes so strange and unreal to the layman. By watching this method in action and seeing its success, however, we hope you'll feel more at home with it. And there is another reason why science, physical science, looks so strangely distorted at first glance, and that's the use of mathematics. Look, how does mathematics come into science? A true picture of science and scientists must explain it. Of course, our programs are not courses in advanced mathematical physics, but we shall and must show the power of mathematical reasoning, how it helps to see through the appearance of things to the underlying simplicity and unity, namely to physical law in mathematical form. I think you'll see in the weeks to come that mathematics is merely a tool, a convenient method for thinking abstractly. And in this, it's not so different from other methods of abstraction. For example, in art, how would Pablo Picasso analyze a material of observation? As an artist, Picasso begins with an ordinary picture of an ordinary bull as it would appear in the world of ordinary impressions. And then, in successive steps, Picasso abstracts from this animal a more and more refined outline. And finally, he gets to the essence of the animal's strange mixture of grace and power. The apparent distortions of nature in the language of visual art is of much the same kind as this apparent distortion on nature placed by mathematics, the language of science. Among the other points which we want to make in the coming weeks, there's one in particular which I think is very important. It's the way in which science and technology are connected. The products of technological research, they are all around us. Television is just one. Think of the others: gasoline, vaccines, synthetic materials. We have not only grown used to them, we have come to entirely depend on them. They are part of our lives. But by and large, science has not been assimilated into our culture, although it is the necessary predecessor of modern technology. Most thoughtful people believe that this is a particularly dangerous situation in an age where the intelligent citizen must act on great problems involving science and technology. On several occasions, we shall look at this modern situation, and on one, at an 18th century occasion, where science led to very practical results.
About 200 years ago, there was a great deal of smoke in the air. There was smoke in the streets. And lots of smoke indoors, too. It seemed very natural at the time. To have heat, you had to have smoke, even if it was troublesome. But as time went on, some people managed to be quite comfortable, to avoid the smoke. You could say they understood the problem, and understanding it, did something about it.
This is a caricature of Count Rumford, and so, in a light-hearted manner, begins a program in which Sanborn Brown of MIT and other of the 10 to appear on our programs will describe the work of Rumford. As you'll see, Rumford at first was interested in what would happen if a tube like this, in which there's water and some chips of amber, is heated. By watching it, he discovered the mechanism of convection currents in fluids, a purely scientific advance. But based on an understanding of convection currents, he invented a whole range of homely but useful devices, the smokeless fireplace and the drip-style coffee pot, just to name two. And the lesson is general. When a scientist searches for truth in pure science, technological applications often follow as byproducts. From the transistor in a small portable radio to nuclear reactors, almost all industrial and engineering devices are developments of some earlier, simpler laboratory tool, used initially purely for scientific research. And notice how simple this tube is. I think this is symbolic too. Making a virtue out of necessity, I can promise you that our demonstration will not concentrate on big, startling devices or effects, but they will more often be quite direct. And I also promise you that the content will not be made more easy than it honestly can be. Some of the arguments are difficult, but after all, we want to tell you about scientists and of science. And this story, we feel, has such importance and such beauty that we would not dare to divert your attention from that which needs to be said.
Next week, we're going to begin in earnest. The first thing we must do is explain the paradox of the scientist trying to learn about nature within the four walls of his laboratory. Isn't there a complete opposition between a real, limitless, uncontrolled nature on the one hand and the abstract, confined, controlled world of the laboratory on the other? A difficult question? Yes. But we will be able to explain a scientist's point of view using just these: a leaf, a steel ball, a pebble, and some critical thinking.
This is National Educational Television.